Cool. Yes, yeah, a couple things happened in the server. One, the bot I use to keep track of all your bond coins and whatnot just decided to crash. That's not my fault. That's the devs. The devs on it, their bot crashed and they had to reset it to a database that was, I think, on the 25th of May. So then I had to manually go through and figure out everyone I had given bond coins to in the last 5 days because I had to re-add them because the levels were wrong. It was nuts. What's up, OP? How many kills to get a gift card? Shifter, if we win, I'll get you a gift card. How about that? I don't care how many kills. We just gotta win. I'll do that. What's up? Let's see. There's Sir Vikenheim wants to come up. All right, cool. All right, I think I got everything. I think everything's working. My voice is fine. Okay, cool. Okay, awesome, great. Let's kick it off. Welcome, everyone, to Office Hours. My name is Dr. Grohl. This is Actual Education, the stream that helps you out with math homework, science homework, all types of fun stuff. It's Wednesday. It's almost June. Can't believe that. We're almost halfway through the year. That's crazy. Easy nerd? Yeah, you think so, dude. I don't know about that. What was actually... There's some cool things that happened in the Discord. Let's see. If we go to our Twitch... Let me mute myself so I don't hear myself. Where do I go to just like my channel? Where's my channel? Can I just see my channel, please? There we go. Okay, yeah, look at this, dude. Look. We hit 500 followers. We hit 501. Where is it? Where is that? Well, there you go. 501, dude. That's dope. I'm very happy about that. I was playing randomly with some people last night, and one of them happened to be a pretty famous streamer girl, and she ended up following me, and then a couple of her friends, I guess, followed. So yeah, cool. We're at 500. That's dope. Happy about that. Always good to have accomplishments, metrics. We're always growing. Okay. What does Paul say? Wow, you're playing a lot of games wow, that's cool, dude. Nice. Okay. All right. Let's see. What's our first question of the day? Let's see. Someone else is posting thing. Yeah. Yes. Yeah. Don't worry. Okay. First one is OP Black. What is the domain of this exponential function? I like this. These are fun. Oh, cool. Nobody has asked about sine and cosine and tangent. Yeah, that's cool. That's a cool question. Yeah, for sure, dude. I can go through that. Okay, OP. What's up? You want to come up to the stage? Did your mic work yet? Did we get your mic fixed? I'm going to send you a mic, bro. Chat. He says chat. Okay, that's fine. We can just chat. All right, cool. This is asking for what is the domain of this exponential function, okay? Do we know what domain is? That's a good first question. Anyone know what the domain is? It's kind of a scary word sometimes. Like domain and range. Yeah. Spread? Kind of. It's kind of like the spread. It's more of, this is related to like all the x values that a function like touches. It's kind of like that's simple terms how I like to say it, you know. Range would then be all the y values that a function touches. Okay. So you can do this graphically. You know, you can look at something and be like, okay, what x values and what y values does this function hit? And then I can show you how you can do it also numerically. So, OP, what would be the domain of this function? What x values does it hit? What's up, Ripple? X equals 2. It does hit x equals 2. I mean, it also hits x equals 0. It also hits x equals 1. It also hits equals x equals -2. I think what you're trying to say, you're trying to say that it stops at x equals 2. Is that what you're saying? You're saying that it doesn't go past this. Is that what you're saying? I think what he's trying to say. Yes. Cool. Yeah. I know it looks like that. It definitely does. So graphically, we would say that this looks like what's called a vertical asymptote. Okay. Vertical asymptotes are lines that the function tries to get close to but can never touch, is what we would say. Vertical asymptotes really only happen when you divide by 0 or you end up doing some weird shit with like tangent or like cotangent or cosecant, like one of the trig functions. But in this case, they don't tell us an equation. They don't tell us anything. They just give us a graph. But they do say that this is an exponential function, okay? When I see exponential function, I'm going to assume this is something of the form of like y equals ax to the b or something is what it is. So what's probably happening here is this is, for instance, let's see, when x equals 0. This is actually probably y is equal to, let me look at that. I think this is 5 to the x is what this is going to be. And we can see why that is, okay? Because when x is equal to 0, what should y be equal to? If we have y is equal to 5 to the 0. Oh, I'm glad you're back, dude. It's all right. Glad you're back. Yes, 1. 1. Yeah, do you see that? You see at 0, this is 1. I'm showing you how I came up with, I know what the equation is, just looking at the graph, okay? What about when x is equal to 1? Okay, let's say x is equal to 1. What would y be equal to? Four? Not quite. It's 5 to the x is the equation. That's what I think it is. So this is 5 to the 1. What is 5 to the 1? 5 to the first power. Help, my Discord door won't work. Oh no. What's happening to your Discord, Teacup? 5 to the 1 is not 6. Nope. 5 to the 1. Do you guys know what 5 to the 1 power is? I know you do. Come on. It's 5 times itself just once. I thought it was 6. No. 5 to the 1 is 5. 5 to the 1 is equal to 5. Yes. Good job, Riplaw. Congrats. Yes. Okay. And that makes sense here, because, no, the way I wrote it, oh, you thought this was a 6. Oh, okay. I can see that. All right. Anyways, okay. So that makes sense here, because you see how, like, at x equals 1, this is also at y equals 5. So, yeah, I'm pretty sure that at the end of the day, the equation for this function is just y equals 5 to the x. This is also going to make sense because as x becomes negative, so as we go to negative values, let's say, for instance, x is equal to -2. What is y going to equal? Do you guys know? Think about that. It's 5 to the -2. What is it? What does that become? Good. Yeah, nobody else got it right. Yeah. But, OP, rip, what happens here, whenever we have negative exponents, I end up flipping this. So this becomes 1 over 5 all to the 2, which is the same thing as 1 over 5 to the 2. This is kind of the trick we do with negative exponents. And so this is 1 over 25. Again, these are important things to know. Like, these are very core exponent rules that we need to be able to figure out. Yeah, good. Yeah. So y is equal to 1 over 25. Yes. Okay. And that makes sense here because, look, when x is equal to -2, do you see how this is like a very small number? 1 over 25, 1 over 25 is basically 0.04. It's super tiny. So that's why, like, as we go more and more negative, this thing tries to basically hit 0 is what it does. Tries to. So knowing that this equation is y equals 5 to the x, you can figure out what the domain is, because the domain is asking you what values of x am I allowed to put in this function. It's like, what are the allowed x values? Okay. There's only a couple times where so usually for a function, you can put any value of x in, usually. Okay. So usually you would say that the domain is what we say contains all real values for x. Or we say this. We say x is contained in all real numbers. This is fancy math speak for being like x can be any number. In simple terms. Okay. Because, yeah, I can put anything in here for x, and, like, it's not going to break anything. There are only a couple cases where you're not allowed to put values in for x. One of those, for instance, is inside square roots. So inside a square root, you can't have a negative number. So this is actually kind of a cool concept here. If I, for instance, had a function y was equal to the square root of x, what is my domain there? Like, what am I allowed to put in for x? Positive numbers. Yes, only positive numbers. Technically 0 as well, because the square root of 0 is just equal to 0. That's okay. So here, if I said, what is my domain? I would say x has to be greater than or equal to 0. This is what I would say my domain is. You can also put this in what's called interval notation, which is something like this, where we say what's the lowest value it can be. So in this case, you say 0, and the biggest value x can be is like positive infinity. That's another way to write the domain. They would do this. They would say it like this. This means x can be greater than or equal to 0, but has to be less than infinity. Infinity is like the biggest number out there. You can't really have anything. These are two ways to write it. Yeah. I think technically 0 is not a positive number. I think 0 is just a number. I think 0 is neither positive nor negative. It is the non-existence of a number. Mm-hmm. You can make this a little trickier, right? Let's say y was equal to the square root of like x minus 3. 0 is undefined? No, 0 is defined. 0 over 0 is undefined. You're not allowed to do that.
No.
Don't do that. Don't do 0 over 0. Bad. 0 over, I think 0 is defined. 0 is just not positive or negative, is what I would say. So, if, for instance, you had something like this, right? This is a common question they could also ask you. You know, they could say, like, what is the domain? And what you know is this has to be greater than 0. You say x minus 3 has to be greater than or equal to 0. And now this becomes like an algebraic inequality you can solve for. So what we do here is just add 3 to both sides, right? You get x is greater than or equal to 3. So if you wanted to write that in this notation, you'd say that, oh, x has to be greater than or equal to 3, less than infinity. Or you could say the domain is this, 3 comma infinity. That's another way to write it. Yeah, lots of cool stuff there. Okay, you can actually see this too, OP. You can see this on a calculator. If we, for instance, one second, let me put my calculator on the screen. My calculator. There you are. Put this. No. Yes. Visual. There we go. Okay. If you graphed, for instance, look, the square root of 3. Let's just see if we graph this thing. Oh, no, sorry. Y is equal to the square root of x minus 3. That's what I'm going to say. Sorry. X minus 3. You'll see this graph only starts here at x equals 3. So the graph like starts here and then does this. This is a cool example of how, yeah, the domain is only values where x is greater than 3. So, yeah. And again, if you wanted to do the, what was it? It was 5 to the x is what we came up as our original equation. Yeah. This you can see, like, this will jump. This will get very big. But if I zoom out, for instance, let's say I zoom out on this. Let's just say we go, like, further and further out. it just keeps going, honestly. It's just it will hit all the x values. It's just the y values become like ridiculously large. So it's kind of hard to see it on a graph. So even though I know on this graph, for instance, it looks like the domain should be less than 2. It looks like it shouldn't go past 2. It's actually all real values. This is all real numbers for x. Because the actual function is this, and it does hit these x values. It's just the function is like way the hell up here. You can't even see it. But yeah, that's how it works. What's up, Albatross? Awesome, cool, nice, good job, OP. Learn about domain and range. Well, we did domain. We didn't do range, but I can do it next time. Yeah, welcome, dude. All right, cool. So you? Yeah, I'm doing cool. I'm chilling. Rent's due tomorrow. I'm not happy about that. The only thing I'm like, oh, the month is over. Oh fuck, I'm about to be poor again. I don't kind of liked, not being poor. Summer's coming up, which is cool. All sorts of fun stuff. What about you, Albatross? Are you going anywhere? Going anywhere fun for the summer? Doing any cool summer plans? Any vacay? I'm gonna go to Michigan at some point. That's gonna be cool, I guess. All right, let's see. We got a science question here. What's up, Teacup? You want to come up stage? Come say hi.
Hello.
What's up, dude? How's it going? What's this? This is this science? Which of these values is most responsible for changing the boiling and freezing points of a solvent? Ooh, I like chemistry. Chemistry's fun.
I had my final today. I probably failed.
You failed chemistry? Uh-oh.
No, I probably failed my final.
What final?
Sure,
final for what class?
I had a final in science today.
Oh, okay. But this is one of the questions? Or like one of the questions?
No. Yeah, similar.
Okay, that's cool. Says, which of these values is most responsible for changing the boiling and freezing point of a solvent? Okay. That's pretty cool. Uh-huh. Oh, wow. This is fun, actually. Okay. Okay, here's a good question. Why do you think things change the boiling point and the freezing point? What happens when something, like, boils? Or, like, freezes? It's kind of a good question. So things are changing between states is what we say. So, for instance, when you have something that's in like the liquid phase, and then we have it going into the gas phase, right? This process is called boiling, is what it is, right? So usually what you have is you have some liquid, and you got these particles, and they're bouncing all over the place like crazy. They're like, oh shit, get out of the way, Okay, cool. And then eventually, you see this when you boil water, right? Do you see like the bubbles come up and whatnot? You ever seen that? Ever seen the bubbles?
Yeah.
Yeah, phase change. Good. Yeah, this is called a phase change. Yeah, I can go more into depth of like, because technically there's a difference between heating and boiling. Like heating is getting it to the point where boiling can happen, and then that's called like heat of vaporization and whatnot. There's a lot more you can go into it, but you're not into that yet. But anyways, yes. So what boiling does is gives these liquid molecules enough kinetic energy that eventually they escape the liquid that they're stuck in. And what that ends up happening is related to something that's called like vapor pressure. Okay. Vapor pressure is like the pressure of like the gas above here and whatnot. And this is actually very cool. This has to do with do you guys know whether it's harder or easier to cook something at high altitude? Do you guys know? It's actually yes, this is chemistry. This is chemistry. But it's also kind of physics. I mean, chemistry is all harder. Yes. The question is it easier or harder to cook something at high altitude? Like if you go up into the mountains, or for instance, you go up to Denver or something, right? And yeah, the question is at higher altitudes, it is harder to cook things. Does anybody know why? It's actually kind of a cool thing. Because of air. It is because of air. Yeah, it's because of the air pressure is what it is. It's the atmospheric pressure is what we say. So there's a cool thing because Teacup, you live in Florida, I live in California. We live in like pretty flat places, right? But if you go to higher places, like let's say Denver's pretty high, both metaphorically and literally. There, because I think they're up like a mile up. I think they call it the Mile High City or something. Yes, but when you're at higher altitudes, the atmospheric pressure is less. Okay, which is pretty cool. So the pressure of the air up there is less, and what that does is when you're So here's a very cool thing. So boiling occurs. Because higher temperatures give particles higher velocities.
Yeah.
And then when they're going at higher velocities, they can escape the atmospheric pressure that's trying to keep them as a liquid. You always have this like atmospheric pressure that's pushing down on the gas particles, trying to keep them as a liquid. And so if you heat something, you end up making the particles move faster so that they break that barrier, and then they can become a gas, okay? Now, what happens at higher altitudes is this atmospheric pressure is less, so you don't need as much heat and you don't need as much speed in these particles for them to break free, okay? So, yeah, and it's not because of less oxygen. It's what happens is water boils at a lower temperature at higher altitudes because you don't need as much heat to give the particles as much velocity to escape. Like the atmosphere at higher altitudes is weaker than it is at lower altitudes. And so you don't need as high of temperatures to get it to boil. And so why your food then is harder to cook is because anyone made like ramen or like mac and cheese or something, or I don't know, you like boiled chicken or something. I don't know. You guys probably just microwave all your food, but no. But yeah, if you cook anything with boiled water, for instance, like ramen or whatnot, the water when you boil it will not be as hot as if you boiled it down at sea level, and so as a result, it takes longer for you to cook your food because hot water isn't as hot. Like boiling water isn't as hot. Yeah.
Huh.
Yeah, it's pretty cool. It's why, it's I remember when I did a lot of Boy Scouts and like camping stuff, and like as you go further and further up, like it takes longer to like cook your food because you're like, oh man, the water isn't as hot. Yeah, it's kind of cool. You're so good, teacher. World needs so many people like you. Cool, man.
That's dope.
I appreciate that. That's dope. Yeah, I appreciate that, man. But anyways, this is one of the aspects of boiling and whatnot. It's kind of a cool little fact. But okay, so what prevents something from boiling is anything that would keep these particles closer and closer together. Okay, so if these particles were heavier, right, then it would be harder for something to boil, right? Because now you need to put even more heat, even more like you need to raise the temperature even more of these molecules to get them fast enough to break free from the atmospheric pressure, right? So that would be like the molar mass is what I would say. The molar mass will definitely affect the boiling point. If something is heavier, it's going to take more. It's going to take a higher temperature, I think, to get that thing up to speed in order to break free and boil. Weight of the solute particles. I don't know if that really matters. I don't think it does. The solute are like these things. It's like salt. I don't think that affects the boiling point. Well, this is a problem. They say the most responsible because like it will affect it a little bit because the more solute particles you have in there, the more like bumping around happens. The number of solute particles that does affect it as well because again, if you have more solute particles in a liquid, then there's going to be more bumping around and whatnot. And then electronegativity. That's a cool one. Electronegativity actually is important. Electronegativity has to do with what's called the I think they call these the dispersion forces, or no, dipole. Dipole forces. Which is basically molecules will attract to each other based on like how electronegative they are individually. Anyways, okay. I think the most responsible. Wait, I think it's gonna be the molar mass. Do you know what the answer is, Teacup? I think it's the molar mass.
I do not know what the answer.
Don't know what the answer is. I think it's the molar mass. But here, we can always look this up. You know, I'm curious.
No, I think I have this. Let me just look.
Chegg is great. I love Chegg. What is the what affects the boiling point problem the most? Let's just see. I'm curious. Well, yes.
I don't have the answers.
Oh, you don't? Okay. Well, okay. I know adding a solute will definitely add it. Will definitely change it. But they said which one will change it the most. I don't know which one changes it the most, honestly. I think it's the molar mass. Any other like chemistry people? Any big chemistry buffs? I only got my PhD in physics, you know. But I've done a fair amount of chemistry. I do like chemistry. I think it's the molar mass of the solvent. What is electronegativity? That's a cool question. Yeah, no, let me go over real quick over electronegativity. Okay. Okay. There's a big chart of this. Let's look it up. Electronegativity chart. Yes. Here we go. Want like a picture of it. Want a picture of it. Yeah. Yeah, it has to do with they call it electron piracy. I like this. This is actually a cool definition for it. Yeah. Yes. Oh, cool. Okay. All right. So every atom, for instance, has what's called like an electronegativity. Here's the periodic table is pretty cool also because it explains a lot of things like trends and whatnot. And you'll get into this, Teacup, when you do more chemistry. So anyways, this is a table of like the electronegativity of different elements. And what electronegativity is the ability for an element or an atom, to steal an electron, is what we say, okay? And usually what happens is more electronegative things will steal from less electronegative things. These are like the, these are the pirates and these are the poor, I don't know. Who do pirates rob? Captain, what's that movie where he's like, I'm the captain now, dude? Captain Phillips. Captain Phillips. You guys don't know that meme, Captain Phillips? Yeah. Okay. The classic example here is, say, for instance, we have NaCl. Does anyone know what NaCl is? Sodium chloride?
Yeah.
What is it?
It's salt.
It's table salt. Yes, sodium chloride is table salt. Yeah, this is what I put on all my food to make it taste good. Yes. Anyways, if you were to draw, let's say, the electron structure for sodium. So sodium has 11 protons. So it has 11 electrons, okay? And I'm just going to draw what's called the valence shell. Valence shell means like the outermost shell of electrons. So here you have sodium just chilling, okay? And then that's going to be in the N equals 3 shell. We're going to put here. This stuff is a little bit more advanced, so, but I'm going to try and like just get the basics from it. So sodium, because it is here, has what we say is 1 valence electron. Whereas chlorine, so this goes 1, 2, 3, 4, 5, 6, 7. Chlorine has 7 valence electrons. So let's draw the two of these. So here's chlorine. Oh, and actually, you know what? I should draw all of them. I should draw all of them here. This is N equals 2. Here. And then we'll say this is N equals 1. Okay. It's got 2 electrons there. It's going to have a full 8 here, right? 2, 3, 4, 5, 6, 7, 8. And then it's going to have 1 electron out in the outer shell. Chlorine's going to have 7 on its outer shell. And then inside that, it's got another 8. 3, 4, 5, 6, 7, 8. And then inside that, it's got 2. Okay, cool. These are two atoms, is what we say. Okay. Now, when things like bond and whatnot, they usually always want to have either 8 electrons or 0 electrons. Well,
Yeah.
having 0 means
8.
that you just get rid of this shell, and now you have 8 in the n equals 2 shell.
You always want to have at least one. They only want 1 full valence shell.
Good, exactly. Good, yeah, 1 full valence shell. So, and this is
Wait, this is still my question.
It is still your question. It's kind of your question. Yeah. It's Albatross was asking about this. He asked about electronegativity. So,
Okay.
anyways, so sodium has 1 electron in its valence shell, whereas sodium chloride has 7. Okay, and like Teacup said, right? So this is 7 valence. This has 1 valence. All atoms really want to have a full valence shell. So sodium would much rather get rid of 1 electron and then have a full valence shell, and chlorine would much rather take 1 electron and then have a full valence shell in the outer one here. And this is also explained in terms of electronegativity. This has like an electronegativity of 4, I think, basically. Like, what does chlorine have? Oh, 3.16. Is that what it says? 3.16? Yeah, 3.16. Okay. Whereas chlorine has a valence electronegativity of, what is it? 0.93. Yeah, good. Okay. So, what ends up happening is when sodium and chlorine get together and they meet up, the chlorine, because it is more electronegative and because it would much rather just gain 1 than lose 7, this will end up stealing this electron away to be with the chlorine. And that's also representative in what the in it having a higher electronegativity. Higher electronegativity means it will steal electrons away from the lower electronegativity thing, which is the sodium in this case. So when Na and Cl bond with each other, Na tends to give an electron away, and then Cl will take that electron from it, and it'll be like, hey, that's mine. and then they're all happy. Cl has a full shell, Na has a full shell, and then they live happily ever after as good old table salt. Yeah. Oh, you have a different name in Turkey? What's the name for it? That's kind of cool. Cool question, though. Nice. Yeah, it's a cool question. How'd your exams go? Didn't you have some exams, Albatross, you said, right? You had some big exams coming up. Okay, let's see. Next question. We had one in the chat here. Nobody said, could I answer briefly during the stream? What is sine, cosine, and tangent, and what are they used for? I know how to calculate them, but I don't really know what they are and where they are used. Okay, cool. Yeah, it's kind of like what's the point of all this? I remember I had a realization of this one time on like a trip. Sine and cosine are pretty cool. Sine and cosine just describe things going, for instance, back and forth. They're used for what we call is like simple harmonic motion. So an example of this, for instance, would be if you had a spring and you had a weight on it and like you pulled it down, and then this thing would oscillate up and down, back and forth. The way that it would do that is also the same that a sine and cosine function looks like the position would be. So sine and cosine are and they're actually kind of basically the same thing. The only difference is the phasing. So for instance, sine looks, here, let me do different colors. This would be an example of sine, okay? And then if I wanted to see what cosine is, cosine would look like this. I gotta get all my pictures right. No. I had it. Fuck. Let me think. Yes. There we go. That's what it is. It's hard to draw them on top of each other. Oh, electronegativity. Yeah. Cool. This is cosine. The cool thing about sine and cosine is that these are really just like off by what we say is like a phasing. Like they're just slightly off. Right, yeah. That's the difference between sine and cosine. But they both describe the same thing, which is going up and down but in like an oscillatory motion. And a lot of things in nature do this. Like waves, sound waves, for instance, behave like sine and cosine. Like I said, springs, pendulums. Even if, for instance, you were to look at, this is the coolest one, is if you were to look at going around in a circle. Let's say you were traveling around in a circle at a constant speed. Yeah. Let's say you were just doing this. Let's say you where is it? Let's say you were just going around this way. Okay. If you wanted to, for instance, say you're going at a constant speed. Say we're going like a constant like 10 miles an hour. Driving in a circle, and I wanted to track what my x position was as I went around this circle. What would you end up getting is that x position would always be equal to, in this case, it's the radius, and then this would be cosine of theta, where this is the angle that you end up making with the axis. Can
you hear me?
I can, just barely, Ethan, yeah. Well, this is 2D, it's 2D albatross. No, now I can hear you, Ethan, you're good. So that's why cosine's cool. Cosine will pick out what the x position of that you are as you go around in a circle. That's how it can be used in real life in that way. But then the common one they always have you guys learn is just solving right triangles. So a lot of times what it is there's some building that's like some height here. You know that the shadow, right, is this long. Like say this is like the shadow. And if, for instance, you know the angle here, if you know this angle, you can then figure out the height. If you know this and this, you can figure out this. Or if you know this and this, you can figure out this. And this all comes to using sine and cosine is what it is. In this case, if this is theta, this ends up being called the adjacent. This ends up being called the opposite. And we would say that like the tangent of theta is equal to the opposite over the adjacent. And this is some nice math stuff you can solve with. It's cool. Yeah. I could go there. Sine and cosine, like, and tangent, all the trig functions have so many applications. Honestly, like, I could spend all hour talking about them. But these are just a couple of the brief ones. Hopefully that, like, kind of answers your question. But yeah, if you have, like, a specific question about, like, sine and cosine and tangent, feel free to ask me, dude. I'll or if you have, like, a specific, like, field you wanted to know, like, where is it used, I could tell you. It goes everywhere. Anything in, like, physics, math, like, whatever. What is your opinion on MATLAB? Ew. MATLAB is expensive. I'll tell you from my experience in grad school. If you were a grad student who only knew how to code in MATLAB, they kind of gave you like the stink eye because they were like, hey man, you could just do all this in Python and we wouldn't have to pay like $10,000 a license for it. I learned a similar language. What I learned is called, because I was in plasma physics and everyone loves this language. It's called IDL. They're the same almost. Like MATLAB and IDL are very similar in that they were languages that were developed for analyzing data and doing various like mathematical things. And they have a lot of cool built-in functions like Fourier transforms, all sorts of stuff like that. So yeah, I learned IDL because that's what my field was really heavy into, and a lot of the grad students before me had written a lot of their routines in IDL, so It was like, you might as well learn IDL. But as I was graduating, it was interesting to see that the department was moving away from that, because programs like this, IDL, MATLAB, and whatnot, are expensive to license. They're expensive to run. And honestly, they're not that much better, or more so that Python open source packages have been getting a lot better. That universities and departments would much rather you just use Python, because Python is free. You don't have, all this stuff's open source. So, the one for, if anyone ever wants to go into plasma physics, it's actually kind of cool. It's my old mentor at UCLA is the head on this project, but it's called Plasma Pi. So what they're doing is they're developing all these cool like routines and packages and whatever classes that you can use in Python to do specific like plasma physics calculations. And they're really cool. Yeah, here's like the documentation. If anyone has used Python, Python has a really cool thing called like the units. They have like a units package, which is like super dope. I remember seeing it for a second, but you can basically give it any number and tell it what the units are, and then say, hey, run this in another set of units, and it'll do it. And I know that may seem simple if you're just doing like meters to feet and whatnot, but when you start getting into plasma physics, it starts becoming like CGS versus like imperial units. It's just KGS. It's just like, oh, is your temperature in Kelvin or is it in like electrovolts? And I'm just like, fuck, I don't know. Like, then there's GNU octave. What's octave? Well, let me check that out. What's GNU octave? Oh, this is therapy. I don't want to go to therapy. GNU octave. Oh, scientific computing. Okay, cool. It's a completely different language. Okay. And it's compatible with MATLAB. Oh, that's cool. That's pretty cool. Yeah. Yeah, GNU just means what? Generic something user license or something? Remember, GNU stands for something in Linux. Yeah, it's just a bunch of free stuff. I remember GNU. GNU's not Unix. Oh, okay. This is one of these like meta things. Oh man, that's too funny. Yeah, MATLAB alternative. Yeah, that's cool. That's cool, man. Yeah. Yeah, that's my opinion on MATLAB. MATLAB's expensive. Don't really learn it. If you need to do anything, just learn Python. I guarantee you, your advisors, your university, everyone will. Plus, like, if you know how to code in Python, you have skills that can get you hired in so many other jobs. There's so many other jobs that are like, oh, you can code Python? Great, we'll hire you because you can code other things. Yeah. Super cool. All right, let's see. Who's the next question I got up on the screenshot? I got Habib or Riplaw. Okay, here we go. I don't know why I pressed on 1/4 times 64. You have AI assignments in Python? Yeah, no, I totally get that. Yeah, that's totally a thing. All this AI stuff is crazy. I can't keep up with it. It's just like there's always something else coming out. Although I feel like some of it starts becoming very I don't know, kind of like buzzwordy. One sec. I want to show something funny. It was what was it? Instagram. Oh well, I gotta be on that Instagram. I wonder if I have it actually. It was an AI post. I'm trying to think what it was. Let me see. Yeah, this one. Is their account gonna be private? Oh, it's not. Yeah. Where is it? This one, dude. Dude, I love this meme. This meme is too good. Is it ever too late to start learning code? No, never too late. But I thought this was a funny one. This guy's like, I can suggest an equation that has the potential to impact the future. E equals MC squared plus AI. Says it combines Einstein's equations. By including AI, it symbolizes the increasing role of artificial intelligence. I was like, what? Like, chill, dog. And then I love how the person who responds to this has a physics PhD from MIT and Princeton. And it's just like, what? Like, stop. Yeah, I feel like some of this AI stuff becomes like too many buzzwords. I'm just like, all right, chill, guys. It's like the whole NFT stuff. Like, do you really want to pay that much for like a picture of a monkey? Like, what? Chill. What's up? Where's Riplaw? Is Riplaw here? Rip, you want to work on your equation? On your question? He's not here. I'll do Habib's. Habib's looks fun.
Will you be able to do mine?
Of course, yeah. I'll do yours, Ethan. I got you. Yeah. What was it? What was it? Yeah. Sawyer said he's still got to work on the bot, so he can't do it today. I was like, okay, cool, whatever. I'll just teach more. Okay. Habib, what is this question asking? Is there a question here? Are they just asking for the slope of QS? Did you give me a question with the answer? I think. Yeah. 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 Okay. Yeah, this is kind of cool, I guess. But you know how to do this, bro. What? This isn't hard for you. I know this is not hard for you. You didn't mean to paste that one? Okay, paste me another one. Show me another one. Show me something that's actually like a question you need help with.
Then you can actually do my one?
I can do yours.
All right.
Here, let's do yours right now, Ethan. Wait for it. Yeah.
What if it's too hard?
If it's too hard, then it's too hard, dude. It's okay. Are you still in school? Are you still in school? Like, do you have class right now? Oh, okay. What are you guys learning in school? Because you just did the Pythagorean theorem, right? What do you do next?
We're doing trigonometry.
Okay. You could find one of those questions too. I mean, that would just be more
I've
useful.
already done this. I've done that a lot of times, finding sine, cosine.
Yeah, okay, yeah, you don't need to do that anymore. You're cool. All right. Maybe like law of sines. Have you done the law of cosines yet?
No, we haven't even. I don't even know those. Is there a lot of tangents?
There's no tangents in it, but it is useful.
Also, one other thing. In science, we're learning how to identify equations like synthesis.
Oh yeah. Double replacement, single replacement, combustion.
I think so. And the other one is composition.
Okay. It's actually kind of cool here. Let me do that question for you. Let me do that one. That one I think is more interesting.
Wait, why can't we just do this?
Well, I don't know if you're really gonna learn anything from this one. This is just like a hard one. Like I get it. I can do it, but you're not gonna learn anything. Let me do like types of, because I'm on a chemistry kick right now.
You're on a chemistry what?
Chemistry kick means like
Oh.
y'all got me interested in chemistry. Pretty cool. Yeah. Okay. Cool. I like this picture. It's a cool picture. Yeah, it's pretty dope. Okay. Here we go. Yes, in chemistry we have things called chemical reactions, right? And there's different types of chemical reactions that can happen. Okay. So we could have, for instance, two substances coming together to make one substance. And this is what's called a synthesis reaction. Okay.
You make something bigger, right?
Yeah, you're taking like two small individual parts and you're combining them to make one big thing. That's a synthesis reaction.
Don't you mean elements? Two different elements to make one big element?
Yeah, elements. Yeah, elements is cool. Yeah, elements specifically, I guess.
And then there's composition, where you have the compound and then you split it into the elements.
Yeah, that's decomposition. Decomposition is when you have a we call that a molecule. A molecule is a thing with a series of elements. You have a molecule that's decomposing into two atoms.
Also, but wait, the teacher says it's composition.
It should be decomposition. Rosen says if that happens in the body, it's an anabolic reaction. Wait, anabolic has to do with no, sorry, I'm thinking of aerobic and anaerobic. That's what I'm thinking about. Wait. Actually, I want to know what anabolic definition. I want to know this. Oh, biosynthesis. Oh, that's cool. Oh, anabolic. Okay. I was trying to like think like what is the definition of like anabolic? Okay, cool. Ah, very cool. Okay. Yeah, stuff in the human body. That's very cool, Rosen. That's cool. Anabolic synthesis. Yeah, she's right.
I've never heard of single or double replacement.
Cool. Yeah. No, that's another big one. Okay, so single replacement is when you have a molecule that has two atoms or two different elements. Sorry, it's not gonna be two atoms specifically, and you end up swapping one of them with a single. Is what happens. Yeah. Cool. Oh, thanks for the follow, Rosen. That's dope. Whereas
Also,
double replacement means that they both switch. So usually, like this thing will switch with this thing, or well, this is weird. Usually the first thing switches with the first thing of the other. I actually don't like this example. This should be, for instance, AD plus CB is usually what this is for double replacement.
Oh, all right.
Oh, that's cool. Yes, yeah. Not to be confused with anabolic steroids. Yeah, that is what was coming first in my mind. I was like, anabolic steroids. Yeah, wait, what? Like, are they like human-based steroids?
Also, I've never really gone into single or double replacement. I've only learned synthesis and decomposition.
That's okay. You're learning some new shit right now, dude. All right. There's some cool examples of this. Okay, so there are special types of certain replacements. The example in double replacement, this is also going to be acid-base neutralization. Do you know what like acid-base neutralization is? Have you ever heard of that before? Do you know what like an acid and a base are? Okay. Acid is something like, for instance,
That burns something. It's like something that can burn your skin.
good,
or
yeah.
anything.
This would, for instance, be like hydrochloric acid. Okay.
Oh.
Okay. And then let's say we mix it with sodium hydroxide. This is the same thing as bleach. I believe so. I believe this is bleach, right? Or is yeah.
Mhm.
Halogen displacement, maybe that one too. Yeah, okay. So here's a cool thing. This is an example of a double replacement, okay? Because what I can say here, this is, for instance, like the A thing. And then this is the B thing. And then we're reacting it with a C thing and a D thing. Okay, this whole thing is D. Hydroxide is what it is. Okay. Caustic soda, is it? Is that what sodium hydroxide is? Which one is bleach? Is bleach NH4? Wait, one sec. Bleach. What is bleach? Oh, sodium hypochlorite. Oh, okay, never mind. I thought there was something else with that. What is NaOH? Oh, lye. That's what it's called. Lye. Sorry, I had that wrong. Yeah, lye. What they make with soap. They make soap with sodium hydroxide. It's called lye. Yeah, this is also called, sorry, not bleach. This is lye. Okay, cool. All right, yeah. You're all good, dude. Help your mom. Okay. So, Ethan, what do you think these things do when they react? What do you think they become? If I told you that this is, for instance, an acid-base neutralization, which is a double replacement.
Don't they become like something new?
Something new. Yeah, it's good. But let's think how this is double replacement. So double replacement means that they're going to like swap partners. Imagine this being like, I don't know, some man dancing with some woman. There's another man dancing with a woman, right? And then they're going to swap who they're dancing with. But the man's not going to dance with another man. He's going to dance with a different woman. What would that end up becoming? Not that there's anything wrong with it, but you know.
It's like swapping.
Good. It's like swapping. I'm not gonna say wife swapping because it's a little too much. But they're dancing.
What's
Let's say
wife swapping?
Let's not go into wife swapping.
Just tell me. Just tell me
When people
what that
swap
is.
wives, it's not a good thing.
What? That doesn't even make any sense.
It
What?
doesn't. It doesn't. But like some people are strange. Anyways, so let's imagine you got two couples that are dancing and they want to switch dance partners, right? That's what double replacement is. What would the new compounds be?
Would it be like H-O? What if it was H and A?
No. So H is the A thing, right? So you're good. So this is the man, right? So he was dancing with woman B, so now he wants to dance with woman D, right?
Uh-huh.
So that would become a new compound.
Like,
Mm-hmm.
wouldn't it be something like HOH?
Good. HOH. Yeah, very good. HOH. Okay. There's a cool thing for this. So HOH, hydrogen hydroxide, this is technically the same thing as H2O. This is usually how we write it. What is H2O?
It's water.
Yes, water. Nice. Salty water.
Or you could say like dihydrogen. You could say something like dihydrogen monoxide.
Yes, that's always the funny thing. It's like, oh no, I drank some dihydrogen monoxide. It's like, no, you're cool, dude.
How's
Yeah,
that bad? How's that bad?
I know, because I don't know. It sounds like you drank something bad, you know. Um,
Hmm.
okay, good. So that's partner one. Okay, so then what about the other guy? Who does he end up? Who does he end up dancing with?
So it's NaCl.
Yes, nice.
That's dope.
NaCl. And let's remember, what was NaCl? I did this earlier, right? I did this where did I do this? Where did I do NaCl? Right here. What was it? NaCl? Remember, is sodium chloride. What is sodium chloride?
What?
put-
I can't remember.
You put it on your fries.
You put it on your salt?
Salt.
Oh.
Yeah, it's a salt. So this is a cool thing. This is an example of a double replacement reaction. Ketchup. I put mayo on my fries. It's delicious.
Not really.
Yeah.
I don't think that sounds good.
But this is an example. So this is an acid-base neutralization. If you take an acid with a base, they end up like neutralizing each other, like they kill each other off, and what you get is two like substances that are relatively safe, right? Water and salt. You just get salt water. Isn't that pretty cool?
Yes.
Yeah, cool. Nice. Learn a little bit about double replacement. It's cool. Nice. And that'll help you out, Ethan, when you get to later classes and stuff.
Yeah, and yes, we have a quiz on that tomorrow.
Oh, good. Well, now you know. That's awesome, man. Did I I hope the dancing people like helps with like knowing how they trade and whatnot, you know.
Mm-hmm.
Yeah. All right.
But
Nice.
also, the teacher will say that sometimes he'll give us things that are neither.
Oh, where they're not
Like-
any of the reactions?
Yeah, not like synthesis or decomposition.
Okay. Yeah, that could be an example of something else. Yeah. And then, well, you don't know what they are. I mean, all reactions can be classified as something eventually, but, you know, sometimes they're different ones. What's up, Riplaw? Riplaw's back. Okay, cool. Rip is back.
Also, what are you
What's-
gonna do when they get to 100 coins?
Ooh. Let me think. Let me think about. You are getting up there. Let me come with. I need to probably release another prestige tier, but I also need to figure out what I'm gonna get for those. You know.
Actually, just give me something cool for this.
Okay.
Give me every time you get to 100 coins, you get something cool, like something rare.
Okay. What would be something cool and rare? You let me know. Yeah.
I guess something similar to the vault prizes.
Yeah. Okay. Yeah, we could do another. Yeah, because I have another controller. You want another Xbox controller, don't you?
I mean, I'll take that one there if I can.
All right. Let me think about it. I'll think about putting like a double vault or something. Nice.
Imagine me.
Imagine. Yeah, Radical Weave, there's a funny joke, right? It's like, oh man, there's a whole rhyme to this one. Where is it? It's Billy H2SO4. Yeah, this is it. Oh man, where is it? Billy was a chemist's son, but Billy is no more. For what he thought was H2O was actually H2SO4. It's like, yeah. The reason for this is sulfuric acid. It's not good for you. Cool. All right, let's see what we got. Next set. Riplaw, and then I think Habib's the last one. Okay. Percentages. I like percentages. Percentages are cool. All right. So I think you know what you did wrong here, Riplaw. So let's try and make it. Let's come up with a new question, which is a little bit harder. Okay. Let's say I want to estimate. What do I want to do here? Yeah, this is a good one. 20% of, let's say, $80. That's kind of a cool one. Yeah. Oh, you didn't mean to press that number. It's okay. Well, let's try to do this. Let's try to do this one. How would you estimate 20% of $80? This comes in handy a lot of times. If you guys ever go to the store and you see stuff is like 20% off, and you're like, oh man, well, how much does it actually cost? This is an example of that. This is an example of one we could do. You should be able to do this in your head mentally, like figure out what 20% is. I mean, you could bring your calculator or your phone out, but there's a anytime you need to take the percentage of a number, there's a method to it. Do you know how to do it, Riplaw? Let's see. Where's he at? What was I saying? Okay. Do you know how to take like the percentage of a number? So if I ask for it, well, here, let's start with like a really basic one. Like let's say, what is 50% of 20? Oh yeah, let's get you on the stage here. Yeah, there you go. Come on up. What's up, Rip?
This is improv. This is odd. This is odd.
This is odd. What do you mean this is odd? Habib says multiply by the thingy.
Odd number.
50% of 20? You should know this though. What's 50% of 20? Do you not know what 50% of 20? It's okay if you don't.
I do, but still.
What is 50% of 20? Just tell me. What if I said half of 20? Would that help? What if I said half of 20?
2.5.
No. Half of 20 is gonna be 10, right? Let's say I have $20 and I'm saying I'm gonna give you half, right? Half of $20 would be 10. I'd give you $10, right? You wouldn't want $2.5. Pardon?
Divide.
Good. It has to do. Yeah, that's kind of like dividing by 2. Yeah. So here's the trick with it, Rip. Okay. Anytime you need to find the percentage of a number, what you're gonna do is you need to convert this percentage into either two things. We can either convert it into a decimal, okay, or we can convert it into a fraction. Okay?
Okay.
All right, to convert this to a decimal, this is easy. Anytime you have percentage, right? There's going to be a decimal there's going to be a decimal like right here, right? This would be where the decimal usually was, right? You're going to move that decimal to the left twice. So I'm going to say move.
Oh, I heard about this.
Yeah, you heard about this one? Yeah, move left twice. Okay? So that's going to end up being 0.50. You see that?
Okay.
Okay. The other way is to write this as a fraction, okay? So 50%, okay? Anytime you have a number, like, and it's a percent or something, you can say that divided by 100. So the other way I could say this is 50 over 100. Okay?
It's 2.
Well, it's not 2, so we're getting close. Okay. So
50 divided by 100 is
that's 100 divided by 50. 100 divided by 50 is 2. 50 divided by 100 is... Well, you'll see it. You'll see it. Watch. Cancel the zeros. Do you see how this is 5 over 10? What's 5?
Yeah.
What's 5 over 10? How do I simplify that as a fraction?
You divide.
Yeah, we can simplify it though. Do you see how I could divide this top by 5 and divide this top by the bottom by 5?
Yeah, get 2.
I get 2 on the bottom. What do I get on the top?
0.
No. What's 5? 5 divided by 5? 1. Yeah. This is why 50% is the same thing as 1/2. Yeah, you see that?
Yeah,
Okay.
'cause, like, 50 is a half.
Good.
50 times 2 is like 100. So it's
Good.
like a
Yeah.
half.
So it's like a half. Yeah. So then what I do is I can take either one of these things and I multiply it by that. Okay. So I could either do 0.50 times 20, or I can do a half times 20. Both of these will work. You'll get the same answer. Okay. Doing this will usually require a calculator. Okay. So you'll pull up a calculator and you'll be like, okay, cool. Let's get out of this. Okay, whatever. So you do 0.50 times 20, right? And you see how this would give you 10?
Yes.
Okay, cool. So that would be 10. Or the other way is to do 1/2 times 20. 1/2 times 20 is the same thing as 1/2 times 20 over 1. Do you remember how to multiply fractions together?
Yes.
What do we do?
We like do 20 times 1 is 20.
Mm-hmm.
2 times 1 is 2.
Good.
So
So we get 20 over 2.
now you divide
Good.
and you get to 10.
Good, dude. Nice. Yes. Yes, good. That's one way to do it. You see how you got the same answer here? You got 10 and 10?
Yes.
Okay, cool. Let's go to here. and here we can do your question here. This is actually a pretty good one. Okay, let's do this. All right. Okay, I want to do 74% of 65. Okay.
Yes.
So what do I need to do? I need to convert this 74% into something, right?
75.
So I need to convert it either into a decimal, right? I'm going to show you how to do it exactly, and then I'm going to show you how to estimate it, okay? A decimal or a fraction, okay?
I prefer decimals.
Okay, let's try decimals, okay. So if I want to write this as a decimal, how would I write that? Yo, what's up, Ninja? Sexy Ninja is one of the guys I met last night. I was playing Warzone. I think he was our 500th follower, dude. Getting us up to 500. Thank you, Ninja. I'm sorry. Yeah, we got bugged out with that. That fucking loading screen sucks on Warzone. It like always crashes. It's the worst. They need to fix that shit, dude. I can't believe they still haven't fixed it. Okay, Riplaw. So if I want to convert this to a decimal, right? How do I do that?
Do we like do the thing you put there's like a secret decimal and you go 2 points back?
Good, yeah. We take this and we go 2 points back, all right? So that becomes 0.74.
We can add a 0 in the front if you want.
Yeah, we can add the 0 if you want. That's totally cool. All right, how would I write this as a fraction?
74 slash 100.
Good, 74 over 100. Yeah, very good. All right, you can write this 74 over 100. Okay, cool. Both of these are legit, okay? All right, and then we would take either of these numbers, and what would we do to it to get the percentage of 65? Multiply. What do we multiply it by?
Really? Do 65?
Yes, good. Yeah. Yeah, we multiply by this one, right? So this is going to be times 65, okay? So we have two ways we could do this, right? I could either do the 0.74 times this, or I could do this one. I could do the 74 over 100 times 65, right?
Either way, we're gonna get the same answer.
You are. But do you see how here they say, like, what's the most accurate way? So because these numbers are kind of ugly, you know, like, to do in our head. It's hard to do 74 over 100, right? This becomes like a really big number to do in our head, right? But what would 74 over 100 be close to? What's a nicer number that we know how to, like, divide out of 100?
What is it? 75.
Good, 75, right? So I'm going to approximate this as 75 over 100, okay? Because then how can I reduce 75 over 100 as a fraction?
Really? Damn, I forgot about this.
It's okay. Think about what can I divide the top by that I could also divide the bottom by? What goes into 75 but also goes into 100? OP Black says 75. Yeah, no. 75 doesn't go into 100. 25, yes. Riplaw, do you see how 25 will go into both of these numbers?
I was about to say that.
You got it, dude. Nice. You got it, dude. All right. So what does that become? What if I divide this by 25? What do I get?
Let me do some math.
Okay, I like to think about this in terms of quarters. Let's say you have 75 cents. How many quarters do you have? Three. Yes, 3. Good. This is 3. Okay. Let's say you have $1. How many quarters do you have?
4.
4. So that's why this 75 over 100 is the same as 3/4. Okay. Okay. All right. So that's a nice number to multiply things by. All right. But then we're multiplying by 65. Right. Okay. This is still not the nicest number because I don't know. 65 doesn't really divide by 4 really nicely. what's something that's close to 65 that would be easy to divide by 4?
Wait, what you said? Sorry.
So we're left with here Riplaw, right? So far I'm at 3/4 times 65. Okay? But we want to try to make this easier. And so what I want to do is I want to change this number 65 to something close to 65 that will end up canceling out with this when we multiply it by. You'll see. This is a little bit harder to see, honestly. Because here, let's do if I did it full out. If I did this, right? If I wanted to multiply these fractions, Riplaw, this would be 3 times 65, which is 195, and then this is divided by 4. And this does not divide nicely. This 4 does not go into 195 very nicely. Okay? So here's the trick. What if, for instance, I were to write 65 as 64 because it's close. It's close to 64.
I mean, yeah.
Yeah, he says, yeah. Okay, cool. The reason why this is nicer is because I can swap these. I can make this 64 over 4 times 3 over 1. Did you know that with multiplying fractions, you can always swap the tops and bottoms? You can just swap them around.
From my calculation, I never heard of it.
You've never heard of that? Yeah, no. Okay, dude, yeah, okay. For instance, if you have like 2/3 times 3/2, you know how to do that regularly, right? What would that be?
Yeah. Wait.
Yeah. It's 1 because this is 6 over 6, right?
Yeah, that's 1 then, because they're both
Good.
even.
Now watch what happens. Let's say instead of doing this, let's say I just swapped these around, okay? Let's say I put the 2 over here. And I put the 3 over here.
I think that's still the same.
It's still the same thing, right? I'm trying to grab this thing. Let me grab you. There you go. Okay, cool. Do you see how this is still 6 over 6? But also this is the same thing. You could do the 3 divided by 3 first. This is the same as 1 times, and then what's 2 over 2?
1.
1. What's 1 times 1?
1.
Yeah, right? Do you see? You see how you can just switch the numbers on the top?
Yes.
I think it's technically called like the associative property. What is it called? The commutative property or something? I think it's one of those.
Probably heard of the switch, but forgot.
Yeah. So anyways, so what I'm going to do is I'm switching this 3 with this 64 because do you know what 64 over 4 is? You may not know this one off the top of your head. This is kind of a harder one.
I need a calculator for this.
Yeah.
I'll have to do it.
Okay, I'll let you know. This ends up becoming 16. And then it's just 16 times 3, which is just going to be 48.
Oh.
That's why this is easier. This 64 thing, this has to do with like powers of 2. You ever seen like like flash drives or any memory or hard drives? You ever see that these numbers keep popping up? For instance, like 2, 4, 8, 16, 32, 64, 128, 256, right?
Yeah.
Yeah. These are called powers of 2. So that's what's happening here when you have 64 over 4. You're technically taking 2 to the 6th divided by 2 to the 2nd, which becomes 2 to the 4th, which is just then 16. That's a more advanced trick for you to know. But just know that. If you have like these sets of numbers and they're like multiplying or dividing by each other, you're going to get nice numbers because they're all powers of 2. Yeah. Pretty cool. All right, that's very good. So, do you see how your final answer, right, would then be this one, the quarter times 64? Or sorry, no, not that one. It would be this one, the 3/4 times 64.
Okay.
Because that's what we got. That's what we got right here. That was the 3/4 times 64. Okay.
Okay.
Good.
Can I get a screenshot of this?
Yes, of course. Yeah, of course you can. Here. Yeah, good job. Nice. Here, let me download the page for you. All right, cool. Got it. And then, yeah, I'm going to put this in the Discord for you. Let me see. Where is it? There we go. Can I drag this in for you? Let's see. There. You should, yeah, tell me, you should be able to, if you can read that. You don't need all the 2s and stuff on the bottom, but yeah.
I can read this.
Cool. Awesome, dude. Nice. Okay, awesome. All right, let's do the last question of the day. We'll play some Warzone. Habib, what's up? You still here? Where's Habibi? Okay, cool. Yes, hi. Okay, cool, man. Yeah, let's do it. This is actually related to what LND was asking earlier about sines and cosines. Pretty cool. All right, it says, given that sine is equal to the negative square root of 2 over 2 and cosine is that, find the tangent of theta. Okay. So, this is correct. Tangent of theta is equal to sine over cosine. This comes from, let's remember, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So if I do tangent is equal to sine over cosine, that's opposite over hypotenuse over adjacent over hypotenuse. And dude, this all used to always screw me up, Habib, but like when you're dividing fractions by each other, all you got to do is take the second one and like flip it and multiply it. So I'm going to multiply this by hypotenuse over adjacent, cancel, and you get opposite over adjacent, which is the same thing as tangent. That's why tangent is sine over cosine. Oh, so Katoa, you can say it, dude. Yeah, I have my Nightbot like if you blast all the caps, because some of the kids just like start spamming caps. The Nightbot does, but there you go. Yeah, caps lock is not a cruise control for cool. It should only do that after a couple messages. It shouldn't do that after one. I gotta fix that. Nightbot's always kind of a mess. Okay. Yes. Does that make sense, Habib? I feel like everything is correct. Okay. Well, maybe let's say what's wrong. Sine, cosine, that's fine. Uh-huh. Okay. Yeah, it looks okay to me. One sec. Sine is that. Cosine is that. Sine or cosine, multiply. I mean, technically, this is improper, is what this is. Nightbot's a bad boy, yeah. Okay, what you should do here is you should multiply the top and bottom both by the square root of 3, is what you should do. I think this is probably where they're gonna get mad at you, okay? So tangent of theta is equal to negative square root of, what is it? Negative square root of 6 over 3. And then this is going to be 3 square root of 2. No. So this is going to be 2 square root of 3. Because this is, no, actually, no, this isn't at all. Wait, one sec. No, wait, there's something wrong here. Also, someone's blaring their horn outside. God damn it. Oh! Oh. Oh. You know where this is wrong? Yeah, no. You know where this is wrong? I don't think sine of theta can equal this and cosine of theta can equal this. I don't think that's possible. One sec. Because this is, okay, this is for instance, this is for negative 45 degrees. Whereas this is for, what is this going to be? Cosine adjacent, square root of 3 over 2 is the bigger side. This is going to be for 30 degrees. These are two different angles. Yeah. They're two different angles. How am I getting stumped on this one? Excuse me? So step A is wrong. Check. Yeah, maybe. I'm just, wait. What? Megan wanted to solve this problem. This problem's wrong. You can't have the sine of theta equal that and then the cosine of theta equal that. Because these don't match up as triangles. You want to see why? This is actually kind of cool. All right. Let's say that the sine of theta was equal to negative square root of 2 over 2. Okay. So that means we have a right triangle where the opposite would have to be negative squared. Well, here, let's do it on the coordinate axis here. I just don't think you can even have this. Okay. Sine of theta is negative square root of 2 over 2. That's a tricky question, dude. Okay. That means that this is equal to negative square root of 2 over 2. And then this is equal to 1. Okay. So this has to equal square root of 2 over 2. By, like, the Pythagorean theorem is what it is. So remember, right, Pythagorean says that a squared plus b squared equals c squared. So this plus this will end up equaling 1. Yeah. Square root of 2 over 2 squared plus square root of 2 over 2 squared. Yeah. Will end up equaling 1. Because that'll be 1 squared. That's a half plus a half. I don't like this. My brain is frying. Yeah. I just think the beginning is wrong. You can't have the sine of theta equaling this, and you can't have... if they're two different thetas, then maybe. If this is the sine of theta 1, and this is the cosine of theta 2, I agree with that. But you can't have these being the same theta. What did she do wrong? All the steps are wrong, dude. What? Yeah. I don't think you just physically can't have that happen. Yeah. Tell your teacher they suck. 1 sec. Let me check on check. I'm actually curious. I'm actually curious about this one. Let me see. I'm curious. Given wanted to solve this problem. Yeah, it's not on check. Yeah, no. I think your teacher. Yeah, I do think your teacher just wrote like a bad question. Honestly, this question would be okay if we labeled this as theta 1, this is theta 2, and then this is like theta 3. Well, no, this is yeah. No. No, this is just all wrong. This is just wrong. No, you just can't. You just can't have this, Abib. I'm pretty sure you can't. Yeah, it's okay. Yeah, I just don't think that's even possible. You can't have sine equal that and cosine equal that. It doesn't work. Yeah, I think it's a typo. I think it is a typo. I think the typo is this should, for instance, be square root of 2 over 2 is what it should be. It can't be square root of 3 over 2. This should be square root of 2 over 2. Then that's okay. Yeah, say that's the typo. So the typo is in step 0 because yeah, cosine of theta cannot equal square root of 3 over 2 if sine of theta equals the negative square root of 2 over 2. They're just describing two different angles. You can't have an angle that has a sine and a cosine. Well, yeah, just write this. Instead, you should write down the right question. That's what I would say. Yeah. I love how I forgot high school math. It's okay, dude. It never leaves you, man. Okay, cool. All right. Thank you, everyone, for coming to office hours. I had a lot of fun with you guys, learning math, science. Shout out to the new people that found us today. That's super cool. Always love it. let's see. Today's Wednesday, so Wednesday's Warzone. Monday we play Fortnite, and then Friday is Roblox. If you ever want to know, Wiener, he says, I think they did an update to Warzone today as well. Actually, they nerfed some guns and stuff. I think they nerfed the Cronin. But anyways, yeah. Next stream is going to be on Friday. That'll be at 5 p.m. Pacific, 7 p.m. Central, 8 p.m. Eastern. And then we'll do a golden hour AMA tomorrow as well. So that's a stream where you can just ask whatever you want. Doesn't have to be math or science related. It can be anything, relationship problems. I don't care. Talk whatever. That one will be at 4 p.m. tomorrow. Same time as this one tomorrow. So 4 p.m. Pacific, 6 p.m. Central, 7 p.m. Eastern. All right, let me get Warzone started up. I hope it updated. I hate when this game doesn't update. You'll get on in 10 minutes? That's cool, man. Good shifter. Yeah. All right, let's start that streaming. Okay, so if you want to still hang around and come play Warzone with us, we're going to raid the actual gaming channel. So that's where we play all the video games. And then otherwise, I'll see you guys on tomorrow's stream. Same place, same time and whatnot. Good to see you. Let me know anything. Oh, and yeah, join our Discord. If you guys want to hear about like more stuff we do and win prizes and get notifications for all the activities, like there's our Discord. We'll probably start doing Jackbox games again this weekend. But I'll let you guys know. I'll announce it. All right. Let me see. Rating. There we go. Warzone. Okay, cool. And then if you're in the Discord, just hop on down to the recess voice chat. I'll see you guys down there. Cool? All right. Good to see you guys. Peace. Okay. That should have rated, hopefully. Okay. Let's end this one. I gotta end the YouTube. I gotta end the TikTok. So many streams I gotta end.